Hello, everyone. My name is Ivana, and this is Silvia. We are working together on water resource management in the Department of Civil and Environmental and Geomatic Engineering here at UCL, together with Yevgeny, who unfortunately couldn't come today, and supervised by Dr. Julian Haru. We are basically looking into ways how we can improve the current approach to water resource management in the UK. No, this doesn't work. Okay. Just to give you a bit of background, we are focusing on the River Thames Basin for London, which is about 16,000 kilometers squared, with annual rainfall of only 500 millimeters. Basin is already considered under stress with over-obstruction, with a population of over 14 million. But everybody knows nowadays there is a climate change, and this actually poses a lot of challenges for water resource management, because there is about 19% increase, or not increase, predicted increase in winter rainfall, and 22% decrease in the summer. So the rainfall patterns are changing, and how we are going to manage this, because the biggest demand is in the summer when the rainfall is going to decrease. Also, the population is growing. Thames Water is predicting that in their water resource zone, the population will increase by 25%. By 2040. But also some institutional pressures, such as sustainability reductions, which means the Environment Agency can actually reduce what amount of water companies can abstract their licenses for abstraction. So that's why we are trying to change the current approach to water resource management, because if you remember, in May last year, there was a hosepipe ban, April-May, I think it was, when people couldn't water their gardens, etc. And that's what we want to prevent. We want to deliver the customers what they are paying for. Okay, I need to go there. Okay, it's stretched. Just to give you a bit of picture about the basin, we are looking into the current supply options that are there, such as reservoirs, the Beckton desalination plant, etc. But we want to know what new supply options we can provide, or demand options, which can be considered, such as for example, leakage control, or water mains replacements to reduce the leakage as well. For example, seasonal tariffs to charge people depending on what month in the year there is, etc. So the question is, which supply and demand management options, the new ones, we can implement to improve the performance of the system itself, and also what capacity they should have. So now Silvia will tell you more about what the current approach is. Do you have?
All right, thank you. So deciding what to build, when, and at what capacity is a typical engineering problem, and is called capacity expansion. So capacity expansion models also used in UK for water infrastructure planning, help defining the optimal, the least cost schedule, new supply side, and demand management options for that meet the future demand. Because future demand and the supply estimate is uncertain, water companies in UK consider a safety factor, which is called headroom. This headroom aggregates all sources of supply and demand uncertainty into one annual estimate. Okay, one single objective function is used, which is the minimization of all discounted capital, operating, environmental, and social costs of proposed options, subject to environmental and political constraints. These kind of models are usually implemented using mixed integer linear programs, which use binary variables to represent build, no build decision for supply side sources, demand management measures, and new transfers. Of course, these models have limitations. So first of all, real supply systems are managed according to several criteria like energy use, reliability, environmental performance, while this model monetizes all aspects of system performance and produces one singular optimal least cost solution. Also, maximum capacity of existing and future options are evaluated under a historical draw condition. This means that the proposed solution might be over-conservative or insufficient under different future conditions. These models are also deterministic. They provide a solution that meets the worst supply-demand imbalance under a fixed level of reliability, which means that it's not possible to provide a reliability cost trade-off curve. Also, the problem of non-convex continuous cost function is overcome using fixed cost and maximum capacity for proposed schemes. Okay, despite all these limitations, these models have benefits like their simplicity and applicability to large systems. And the fact that such a model built from UCL has been used to optimize infrastructure investment decisions in the water sector in the southeast of England with almost 20 million of inhabitants as a proof of its ability to plan for real systems.
Okay, thank you. So now, if we consider only one single objective, although we might try to aggregate, for example, the impacts on the environment and socio-economic impacts into this one single objective, they might be hard to monetize. So what we are trying to do is to consider multiple objectives explicitly, and instead of just looking at the costs, consider, for example, the supply deficit, the resilience and reliability of the supply system, the environmental impact in terms of eco-deficit, which we define as the difference between the natural flows and the simulated flows after the obstructions, and also what energy will actual new system require. And also we consider feasibility constraints which reflect Thames Water's levels of service, which basically defines what is the maximum frequency allowed for the failures to occur, which is basically, I forgot to tell you that reliability means the frequency of failures, while resilience, the duration of failures. Okay, but not only that, we need to incorporate the uncertainty into decision making, and what we started doing at the moment is considering 11 future flow scenarios, so considering multiple possible future states of hydrological flows within the basin, and also 3 demand scenarios, 3 possible demand growths, and within that we have to perform some statistical analysis of the objectives and constraints, because we are simulating the system with multiple scenarios. And also we are seeking robust solutions that perform well across all of these futures and satisfy all the constraints. So if we look at the least cost solution, which currently water companies are considering, we can possibly see the bigger picture, because when we add the reliability, we don't have just one single solution anymore, which was there, but we have a curve, a trade-off curve between reliability and the cost. And that's what we want. We don't want the model to say, this is one single optimal solution that you should implement, but we want to provide different alternatives that the decision makers can then trade off. because trade-off happens everywhere in the world. If you consider the time of commuting and the cost of accommodation, you have a trade-off already there if you're working in a city, for example. But considering multiple objectives can give us even more bigger picture, can provide more solutions that we wouldn't be able to see if we were looking only into two. So if we add all the 6 objectives that I mentioned previously, we'll get front that contains many more solutions, and these, each one performs better in one objective than all the others, but you can't improve performance in one objective without reducing the performance in one or more of the others. So there is that trade-off in the decisions. If we want to look at these objectives at the same time, we can add some depth to this plot, and we are at the moment we are adding the energy requirements, and just to maybe make it more how it looks like. So we added energy here, and the arrows here represent the basically the preference. Okay, thank you. Where we want to be in this space, but we can see we can't achieve this solution because there is that trade-off between the multiple objectives. And if we add the environmental performance in the color, here you can see that the best environmental performance is, of course, achieved with the highest investment. But this also requires the highest energy requirements, but at the same time provides the best reliability. And here you can have a discussion. The decision makers can discuss themselves what their preference is, what they want to achieve. But also, each of these points represents a mixture or a portfolio of those supply and demand options. And you can look at how these options actually influence your system. So here, we are looking at the pipe repair campaign, or the mains replacement, basically. And the red color shows portfolios where this option was implemented, the blue color where it wasn't. And you can see straight away that it divides the Pareto approximate front into kind of two nice curves. But then, if we look, if we add another option, such as the reservoir, the cone pointing downward shows when the reservoir was implemented. And you can see straight away it was implemented all the time. So here is a suggestion that the reservoir can be considered robust if we consider uncertainty. And also, desalination plant, if the cone is bigger, it means the desalination plant was built. If not, it doesn't. And if you look closer, here we have a portfolios where we implement the mains replacement, we implement the reservoir and the desalination plant, and these solutions perform the best in terms of reliability of the system, and also eco-deficit, which was shown previously. But we want to see what its actual impact has against the deterministic approach when you consider just historical flow records. And we can see that the objective space has actually reduced. The translucent points represent the deterministic Pareto approximate solutions, while the full color ones are from the incorporating uncertainty approach. To look closer, we picked, this is the deterministic plot comparing the environmental performance and total cost. And the color represents mutually exclusive options, which were either build a reservoir or implement River 7 transfer. And the deterministic approach suggests that we can find optimal solutions where we don't have to build none of these, or where a transfer, the River 7 transfer, can be implemented. But of course, in the multi-scenario approach, only reservoir is robust and therefore is present in the optimal solutions. So we picked 4 representative solutions from the deterministic optimization, and wanted to see how would they actually perform if we subject them to uncertain conditions. And we can see straight away that the least cost solution and the transfer solution actually don't occur in here because they violate the feasibility constraints when the flows and the demands are uncertain. Reservoir and the best environmental performance solution survive, but actually perform worse against environmental performance than was suggested by the deterministic approach. This way. Okay, that's what I've just said. So what are the key points out of this is that considering multiple objectives explicitly means that you don't have to try to monetize the impacts, socioeconomic impacts or environmental impacts, and aggregate them into single objective. But also, it provides decision makers with many alternatives instead of just single solution. There is no need of prior knowledge about the system because when you are aggregating the objectives into single one, you have to weight them according to your preferences. So you need to know those preferences in advance. But if you consider them explicitly, you don't, and you learn from the analysis of the alternative solutions what those preferences actually, how they interact with each other and influence each other. Also, deterministic approach can be biased, as we saw, with comparing the picked solutions. And if we consider instead many plausible future states, it can provide robust solutions and also better information for the decision makers to plan into the future. Okay, that's it.
Thank you very much indeed. This is quite promising. It looks like one of those examples where adding complexity not necessarily comes as more uncertainty, well, in terms of solutions and practice orientation, etc. Floor is open for questions.
Hi, I'm Jonathan. I'm from the UCL Energy Institute. So with your sort of multi-parameter optimization, in a sense, would you say that you're making the preferences, which would normally be assumptions, input into the single variable optimization problem? You're basically making a preference explicit in a sense, and that you are sort of saying, you can vary your preferences, and if a decision maker already knew their preferences numerically, it would turn back into effectively a single optimization problem. You always get like a single optimal solution for a given set of preferences.
Yes, in a sense, because when you're aggregating those objectives, as I said earlier, you need to give them weights. So you need to kind of already know what those weights will be. While in here, you don't need to know which of these objectives will be more important, because you can judge that after the optimization process and look at actually this objective might be more important than this one, what we thought earlier, because it influences our system in different way than we thought it would, if that makes sense.
But in the end, don't you have to have, like, isn't the choice of like which dimensions are more important, doesn't that become a subjective choice in any case?
Yes, but it becomes the objective after.
Okay, yeah.
Not before the optimization happens, but after. And that's what we're trying to achieve.
Okay, thanks.
And my impression would also be that you could hand it over to those making decisions, because it's more explicit. It's like revealed preferences and a number of criteria, and
Yes.
it's probably not you making the decision or
Yes.
the planner making the decision, but any kind of assembly, policymaker, public administration, stakeholder dialogue, or whatever. Okay, thank you. Yep, there's more.
Hi. If I understood correctly, you in the figure you were showing, adding 0.1% of reliability could cost up to 2.3 billion.
Yes.
And I mean that doesn't make sense to me as long as I don't understand what the cost of that 0.1% of lack of reliability is. If you know what I mean.
Yes, that's to do with how we actually treated, what statistical analysis we used, which might not be the best one because we took the average value of the reliability across all of the scenarios. But it depends what scenarios you actually choose as well to include in the optimization, because there might be one that will cause the system always perform the worst, while most of them might make it to perform okay. And if you choose the average value or the expected value, that wouldn't necessarily reflect the worst performance of the system that could possibly happen. So that's, again, another thing we need to consider better in order to represent the behavior.
Yeah, but what I was getting at as well is if, I mean, it would, for me, if I was a decision maker, and I'm not, and I don't understand the whole process very well, but if I was a decision maker and I was presented with that information, I thought, okay, I have to pay 2.3 billion to improve 0.1%. To me, it would make sense if losing that or adding that 0.1% costed me 2.5 billion. That makes sense?
Yes.
Do you have that information as well? Is that part of the optimization as well, or?
Well, if you look at the plots themselves, for example, this one would be the best. That's what these actually can provide you. It can you can see that you can achieve this reliability for around 2 billion, but then suddenly you have to invest a lot of money to actually improve the reliability only a little bit. This what the trade-off curves give you, the information that you can compare individual solutions and see what you need to do in order to improve performance in one of the objectives or two of the objectives that you care the most about, for example. Does that answer your question?
Yeah.
Thank you.
Well, in a way, probably it also reminds us that there is a need for a dialogue between those who plan and those who do the multi-criteria magic, because it's not only about bullets, but also about the information that is hidden behind the different points. Okay, thank you very much indeed.
Thank you.